Hello, I'm your host Deepak Shankar. I would like to welcome you to Mirabilis Design's webinar series on hardware and semiconductor technologies. Today's topic is evaluating UCIe-based multi-die SoC to meet timing and power requirements. Today's agenda is going to be a little bit of a mix of technology, application, and analysis. Let's talk about a system level architecture analysis of UCIe-based multi-die SoC. This is the listing of all the libraries within VisualSim Architect. There is this challenge that's going to come up where there's going to be a lot more interaction in future designs. So a variety of analysis can be done with VisualSim. So today's agenda is going to be a little bit of a mix of technology, application, and analysis. We're going to start out talking a little bit about UCIe and then introduce you to system modeling with UCIe. How do you create models on UCIe and analyze them, look at different types of examples, and finally, an overview on some of the use cases. If you take a look at the UCIe background, there is really a die-to-die interconnect that has been around for about 5 to 6 years now. The whole goal is, if you're trying to package a large number of functions running at different clock speeds, different types of dies with different processes, you really need a mechanism to combine them into a single package. The motivation of having multiple dies in a single package is because the size of the dies, the process nodes, the clock speeds are both sufficient, but at the same time not required for certain applications. So really integrating multiple dies into a single package is the future. Now, when we look at the chiplet challenges, the first and foremost is most of these communication between adapter to adapter is very slow. That means very high latency and consumes too much power. There was really no standard to handle all the routing, signaling, multiple clock domains, and even things like cache coherency, supporting multiple protocols like streaming versus PCIe, things like that. What really came out of it is the ability to look at how do you study these things? How do you determine if it really makes sense to have a die-to-die interconnect or have one monolithic die? The exploration needs really a mechanism to predict what is the latency, the peak throughput, the power consumption. But at the same time, you need tests to see, is it really feasible? Can I say put all my compute resources on one die, put the memory on the other die, the analog on a third one? If I do that, what happens if I have a failure? Or for example, if I have too many concurrent requests, how does that need to be scheduled? And what's the quality of service algorithms I need to deploy in this particular design? The future is here today, and it's done by Universal Chiplet Interconnect Express, or short UCIe. It's really an industry standard and an open industry interconnect standard that provides a customizable level integration of chiplets. One of the things you'll notice is that PCIe 6.0 is used extensively, and the reason being that the original interconnects between chips is really PCIe 6.0. To keep with the same methodology, keep with the same interconnects and other protocol integrations, it was felt best to follow the PCIe 6.0 standard. The whole goal was to make it both interoperable, but at the same time work across process nodes and also be backward compatible with designs that have used earlier nodes that did not support the UCIe. The goal is everything that everybody wants: high bandwidth, low latency, power efficiency, and of course, costing. What does it look like? When you want to implement the UCIe, you're really saying, okay, I'm going to put all the compute, say my AI engines or my GPUs or the processor cores, or running a very advanced process node into certain dies and make them really performance critical. And then the other ones like memory, IO control, analog, that can be reused from earlier designs maybe in a much earlier process, maybe N-3 or even N-4, that can continue to be reused and attach them to this UCIe interface. Of course, there is this challenge that's going to come up where there's going to be a lot more interaction in future designs where even the AI engines are going to be distributed across multiple dies. There's going to be a lot of communication between them, data transfers, coefficients, signaling, a lot or control. A lot of them is going to go across in the future, which will require deterministic latency. Can the system provide that? That is where you want to look at optimal designs where you do the accurate assignment of different types of resources, both pooling the resources or even sharing resources. Now, UCIe is expected to have 4x the bandwidth of PCIe 6.0. So if you remember, PCIe 6.0 is what we use to connect FPGAs, connect SoCs, and with UCIe, theoretical bandwidth is 4x. Now, why do I say theoretical bandwidth is 4x? It's because the actual bandwidth has a lot of dependencies. Things like are there continuous data being available? What is the buffer size of transmitter? The replay buffer, because of all the PCI-based error checking and CRC and things like that, the replay buffer plays a major role in what is the actual effective bandwidth you can get. I'm not going to go into this, but just to show you what are the different data rates available and what are the different densities available that you can use with PCIe. A quick introduction to how the UCIe works. It's really kind of like a layered architecture where each layer has a very specific set of tasks. So for example, the physical layer handles all the signaling and clocking and the training and manages the sideband. The die-to-die adapter is the one that handles the things like the reliability delivery, the retry mechanisms, the negotiations, all of those are handled. And of course, going up to the protocol stack, which is handling all the data communication protocols, it really becomes a FLIT, very similar to the PCIe. We're using a FLIT. In this case, it's you can use, say, a 256-byte FLIT. There are flow control units. So this is an important consideration. There's flow control that defines what the underlying transfer mechanism is and who's responsible for the reliable transfer. So as you can see, these different layers play a major role in ensuring both the reliability of the system, but also at the same time maximizing the bandwidth available. A little bit about the packaging, so that's UCIe is all about the packaging. And this is where exploration starts becoming a challenge. So if you look at it, you have standard package, you have advanced package. If you have multiple nodes, you get a different number of lanes versus if you have a single module. If you have multiple PHYs, the logic provides for greater data transfer with better scheduling. But at the same time, it also impacts other things based on the number of protocols and things like those. What is the transition from monolithic SoCs to UCIe looks like? So for example, if you look at this, you could have an AXI bus, or you could have, say, a network on chip, or you can have any other, or a token ring type architecture with all the devices connected with a single area where the actual memory itself is located. With the PCIe, and the UCIe connection, you can have all the interfaces on one die, the analog on another die, possibly the memory on a third die, and all the processing nodes on one or more dies. Now, if you notice here, the important consideration is all of them are using PCIe Gen 6. And there's a reason for it. When we're doing the exploration, I'll be discussing why that is a major consideration. Since we talked about PCIe 6.0, let's talk a little bit about, what is a commonality? First and foremost, they are sending data in FLITs. So you send it as packets. The difference is PCIe has a fixed packet size of 256 bytes, while UCIe FLIT is really based on the sender and receiver protocol. The other one that's common is the fact that you have a credit-based flow control. So it ensures that there's no loss of data. The retry mechanism ensures reliable communication. And for that, they use the ACK and the NAC to confirm good reception. So there is a selective and standard ACK options based on what your requirements are. Of course, there's also a CRC checksum to ensure that you're getting the right data through. You also have the bandwidth depends, just like PCIe 6.0 depends on the number of lanes. Of course, the number of lanes has an impact on standard versus advanced multi-mode. And here's where you can have multiple lanes. So for example, for reliability purpose, you can have extra lanes that can be brought in when your design has a loss of data or has a failure or things like that. Let's talk about a system level architecture analysis of UCIe based multi-die SoC. So what happens is you start with a multimedia. In this case, we're selecting a multimedia application. This is a traditional one that is included as part of the UCIe templates, and it's provided by Intel. So here, if you look at it, you will notice that all of them are connected through PCIe 6.0 interface. They all have local memories. This one here uses a CXL 3.0 for an SSD, but it's an off package. So for that, you have something called the UCIe retimer. Now, the typical questions that would ask, the basic questions is, what should be the transfer rate between all of these interfaces? Because remember, the number of wires have a huge impact on your cost, the power consumption. At the same time, if you have too much of bandwidth, you're just wasting away die space. So a lot of considerations have to be made in selecting the right transfer rate between these different dies. Of course, on the UCIe retimer itself, what should be the retimer timeout duration? So what you're doing is you create a block diagram that looks like this. Once you've created a block diagram that looks like this, the next step for you is to be able to create a model using the VisualSim environment. So VisualSim is an architecture modeling tool that provides you a large number of library components to allow you to create these different types of models. So one of the key components that is in the tool right now, which are introduced, is UCIe. Now, UCIe has its own unique set of parameters. Notice anything from number of modules, remember that's an important consideration for the number of PHY connections you need to have, to like, for example, the retimer, timeout, the number of successive acts, so you can reset those. So even though the standard says 3, you can actually vary those and try different experiments. Buffer, of course, the buffer sizing is a very important consideration. So there's a variety of parameters that are provided, and a big one is really debugging. One of the things is that there's a lot of interaction, a lot of communication, sideband, main band, retries, timeouts. There's so many different things that happen. You want to really understand what's going on in the system. So that enabling debugging provides you all of that information in the in a mechanism that you can quickly read and understand if they had a performance issue or I had a power issue, what was the cause of it. So that debug provides you that information. There's also, you can have an extended wire delay, especially for those that are off-chip connections. So this is, between two UCIe based dies. Now, each one of these are what are called hierarchical components. Within each of these hierarchical components, there are more details. For example, this could be all the different types of IOs like USB or HDMI or Wi-Fi or things, or I3C, things like that. While these could be related to the processor cores. So you could have like the A72 cores or an A53 cores, or some of these could be GPUs, some of these could be AI engines, any combination of those. So you're assembling all of those and then connecting them up or connecting them together using the UCIe interface. So you can see that each one of these modules or dies are each connected to one of the nodes of the UCIe. The key thing in doing any sort of architecture analysis or exploration is really trying to understand what is happening in the system. The debugging information I spoke about earlier is valuable, but at the same time, you also want to know what's the statistics. Now, in this case, we have two types of architecture that we're looking at. One is an advanced package. We remember 128 wires, while this is a 32 wire. So it's a 4 module versus single module. So this gives you 32 gig and this gives you 4 gig for configuration. Now, the key thing is to really understand all the different types. So what's the transfer megabytes per second are you actually using based on your use case, based on your traffic, based on the particular application of that period of time. So you can see what your maximum minimum latencies are. You can see what was there any data dropped as a result of this retimer setup? What was the receive and transmit data? All of this information can be captured in your statistics. Of course, when you're running different types of configurations, you can do comparisons. So here, for example, this one is with an advanced package 4 module. You see it's about 1.2 E minus 9, so about 1.22 nanoseconds across the interface. But here you notice it's almost almost 400 nanoseconds. So you're going from about 1.22 max latency to almost 400 nanoseconds. So it's a huge difference that can be observed between these two packaging. So really you have to consider your application, your use case, your traffic to really understand which one do I need. Of course, there's a considerable amount of cost and power differences between the two. So in this case, for example, it could be that if it's a non-critical application, a non-time critical application, the standard package might be a more than sufficient option, which means that you could be saving considerable amount of dice space, power, and the UCIe lanes as well. So really the statistics need to be studied to come up with what's the best configuration. Let us look at some applications of UCIe-based multi-die SoCs. So the most common one, as you saw earlier on, was a multimedia application where you have high performance, low performance cores. Your GPUs are, all of them on separate cores with local memories. You have your audio video encoders and the IO itself connected off to off package interconnect. So this is probably the most common type of architecture for anything that's not a processor. And this is what most of the designs are being used. So again, the issues come up is, all the details regarding the interfaces here, to really be able to understand, what is the memory accesses between dies? Are you going to be making IO requests? What's the size of these IO requests? How many concurrent requests are being made to the IO from multiple devices or multiple dies? All of those need to be considered. So this is a multimedia application. As you start getting into artificial intelligence, autonomous driving, things like that, the designs are far more complex or complicated. Now you notice here I have an AI engine tiles. I've got GPUs, I've got analog and a process subsystem. So there's no retimers, no off-chip requests, nothing. Everything is self-contained right over here. So now the question comes up is, what do I need to do here? There could be things, for example, what should be the mesh? How much of mesh can we handle if I have to go over to the process subsystem to go get data? So what is the maximum number of tiles I can handle to do the processing? Or for example, within the GPU itself, how many processing engines do I use? How many warp schedulers do I need? How many threads, things like that, and how much a local memory do I need versus having to go to external DRAM? Similarly, right over here within each of the engines, or maybe a common could be a local memory there as well. So you're looking at not just the UCIe backplane, but also the bandwidth, the throughput, the the latency, the power consumption, all of those, and also the configuration, the topology, all of those on both within these different dies plus the die-to-die communication. So now when you looked at the earlier one, the multimedia, everything was pretty much self-contained within its original dies. Here, there's a lot of communication between all the different subsystems. So which means all of these aspects come into play, both die-to-die and within a die itself. So the analysis has to support the ability for you to put a complete SoC together, not just the die or the UCIe or things like that. A third example, which is even still common today, but requires the use of cache coherency. So you have Your cache is connected at the next level to the UCIe backplane that connects to, say, in this case, the LPDDR5 memory. So you have each one of these running on different processes, and you have the caches on these local systems that are then communicating to here. So there's going to be cache coherency. So there's going to be contention. There's going to be signaling. There is going to be routing of data. All of those are going to be happening. So at this point is where you might be considering where, do I need to send all the data here, or is it possible that I can maintain some of the data locally? How does that impact my performance? So not just a cache, but also maybe a buffer of some sort. So it gives you that ability to research those aspects as well in your particular design. Let's look at the design challenges in implementing UCIe. There's a lot of advantages to migrate to UCIe. For example, you can do huge memory transactions, but these huge transactions can be blocked a high priority control access. So for time critical applications, say like in automotive communication systems, these are not desirable. Now, obviously, the big advantage of UCIe is you can have multiple chiplets connected easily and efficiently, reusable of existing technology, including the PCIe 6.0. But the sizing of the resources per chiplet needs to be correct, not just maximize, but optimize the bandwidth usage. You don't want to have more bandwidth than is actually needed. So the resources that are all available need to be really considered to ensure you get the optimal cost of the chip. So data center applications, AI accelerators are where you can take maximum advantage of these multi-die SoCs. Another area of migration is where we're seeing a lot of activity is monolithic to chiplet in smartphones. This is a very efficient mechanism because one of the things is there's always a limited amount of memory available. That's one of the reasons why you see mobile phones advertising the amount of memory that they have. And it needs to be partitioned across these different dies because you want to minimize, I was showing you earlier, you want to minimize the amount of contention that's happening over here to get access to the memory. So, for example, the M1 Ultra used chiplets just to double the performance. So you can see what a huge, remarkable change that is. Those were the design challenges. When we look at the performance challenges, for example, say you have a CXL stack with two protocols sharing the PHY adapter. The data is sent to the flits, but then they need to be alternated between these two protocols. So if one of the protocols suddenly doesn't send data for an extended period of time, essentially a bandwidth is cut to 50%. So these things need to be considered when you're doing your modeling, but also at the same time doing the analysis. If you looked at that first design, you can move from standard to advanced, but the problem is, do you really need all that extra bandwidth? Can you live without that and still apply or still enable your system to get the efficiency that it needs? What happens for cache coherency when you're accessing multiple chiplets in your design where the data is stored at the same address location? How is that information managed, especially if there's a lot of constant reading and writing data to these addresses? The last one, and this is very important, is peak throughput. So we always talk about average throughput, but what about, in this case, a shared resource? The switch essentially is allowing you access to shared resources. How do you ensure or guarantee peak throughput? Some of the future designs they're talking about is AI engines can be distributed across multiple dies. So what happens to your performance challenge there? Let's analyze a UCIe-based multi-die SoC. So let's take the example we looked at earlier, which is the autonomous driving. So for example, what some of the things we might be looking at are, what's my optimal mesh size? It could be 16 bytes versus 32 bytes for the amount of sample size or the data size. Now, the other question is, for the UCIe to be most efficient, you want to go with PCIe Gen 6, but you really need PCIe Gen 6. Is Gen 5 sufficient? Because again, there's a lot of changes, a lot of technology advancements. PCIe 6.0 is very new, so a lot of quality issues can also be there. So really, do you need it? Now, process subsystems, do you use a single protocol stack or a multi-protocol stack? Do you take all the memory and store it in one chiplet, or do we like distribute some of the memory locally over here, like we have done over here? What are the considerations for all of these things? This is in addition to the resource sharing and resource pooling that we want to do, like number of lanes, there's this clock speeds, what is the flit size, all of those considerations also have to happen over here. So if you looked at it, there's design issues within the dies, and then there is design issues around the UCIe interface. So what we do is we build a model in VisualSim using these different components. So for example, over here, you can see I've got the AI, GPU, and processor subsystems connected to memory chiplet, have a UCIe backplane. So if you look at these, this is a hierarchical blocks. So you can see the inside details. So that's a deep neural net. That's a GPU subsystem. And then you can see a 4-core process subsystem over here as well. Now, there's also power information associated with each one of these boxes. So with VisualSim system model, you can very quickly assemble up these systems and be able to analyze the different topologies and different studies. If you notice, each one of these, the GPU, the deep neural net, each one of them has a unique set of parameters that we're looking at. When we look at the statistics, there's a variety of statistics that are being generated in the system. So for example, here you can see what is the latency for the applications running on the processor. What's the power consumption of the entire SoC? What in this case, we're just breaking it down to what's the GPU power. What was the core MIPS? Like what is the MIPS for each one of the cores? There were 4 cores, if you remember. What are the MIPS? Similarly, what is the latency for each of the cores? The AI engine is the one that's making huge number of accesses to memory. So following its statistics is something that's very critical. And you'll notice there's a lot of spikes in the AI engine latency. Now, in this case, if you remember, we are mixing older gen PCIe versus with PCIe 6.0. The flit size, because of that, is going to be lower. You're not going to get the maximum flit size, so which means decreases efficiency, increases latency. So you can start seeing, like what's the overall latency considerations across different ports of my architecture. These are all standard statistics that are provided as part of the modeling environment, as part of the libraries that you get from VisualSim Architect. A key consideration here is really comparing, what happens if I use all 6.0 versus I use some 6.0 and say some streaming protocols. How does the performance efficiency change? Notice here, if you look at this, most of the activity, there's a lot of them that are shooting up right over to closer to 2.5 or 25 microseconds. But notice here, my peak latency, which is only in these few spots, are going anywhere above 15 microseconds, only a few points here. While here, you notice there's a whole bunch and the numbers actually increasing right over here. So it tells me that yes, the PCIe 6.0 does provide lower latency, but again, the bigger issue that comes up are these spikes. Why are there these constant spikes? And is there any way to smoothen out the latency for memory accesses? Because having all these spikes can really cause a lot of performance issues in your overall chip design. Quick introduction to Mirabilis Design. Mirabilis Design is based in Silicon Valley, and we have development centers across the world. We have over 60 companies using software. We've got over 250 designs that have been completed. We do have a few users already using the UCIe IP, which means we're going to start seeing new designs come out with the UCIe. We also have people using network on chip, Arteris Knox, CMM600, AXI buses, and a host of other technologies, both using ARM, NXP, and other products as well. Now, from a milestone standpoint, Mirabilis Design has been successful in winning awards right through its history. Even this year, we got Best in Show at Embedded World. Last year, Best Embedded System Presentation at DAC. 2019, we got no awards because we didn't really have a show to go to. But 2018, we got two shows, both at DAC and at ARM TechCon. Earlier, we won Simulator of the Year. So a lot of innovation awards have been coming to Mirabilis Design for its products. So it's been a product that has really sustained the test of time and at the same time created innovation and new technology year after year. A quick introduction to VisualSim Architect. VisualSim Architect is a system modeling and simulation software and really connects the requirements, exploration, and verification into a single package. So this is an important consideration here, is that you're really tying your requirements to your design. So the requirement says my buffer occupancy cannot exceed so much, or my cost cannot exceed so much, or my maximum latency has to be below this number. That gets incorporated into the VisualSim model. And as a result of which, you can get better quality architecture exploration, better quality optimization. What is unique about VisualSim are the libraries. We've got a huge library of modeling components that allow you to put together system models very quickly. Also, it's a true mixed signal simulation, so you can mix analog and digital within the same model to do power, performance, and functionality or mathematics type analysis. Now, there's a lot of statistics and the documentation that are available from VisualSim, while at the same time, there's also a lot of different types of modeling methodologies, different types of abstractions that are supported by VisualSim Architect. So a variety of analysis can be done with VisualSim. So anything from latency throughput to looking at heat temperature for the power to looking at failure analysis. So for example, even with the die, I can reduce the number of links, for example, or lanes. I could do in such a way that the flit size becomes smaller midway through the design. Or I can have spurious addresses that are being sent across the die to die to see what happens to the overhead in the system as a result of doing something like that. So a variety of failures can be generated. Of course, one of the other key things that can be done is really looking at the software quality as you run this whole die-to-die or multi-die SoCs. You can look at what the response time is for a certain application. You can look at what the memory throughput, memory bandwidth you get for the AI engines, things like that, based on certain software controls or maybe a software function, like say an FFT. How do you optimize the FFT? So looking at all of those kind of software evaluations as well. This is the listing of all the libraries within VisualSim Architect. As you can see, it's a large library of components. As a matter of fact, libraries are constantly being added on a weekly basis. So like this week, we're adding LPDDR5. A few weeks ago, we added UCIe, the production version. So every week, something new is coming out in the tool. New capabilities are coming out as well. So with this, I'd like to thank each and every one of you for attending the webinar, and I hope you were able to get the information that you were looking for from this particular session. I open the door for everybody to ask any questions that you might want, and I'll be happy to answer those questions. We do have some questions coming up. This was a question with regards to UCIe. So to answer this question, VisualSim Architect has created this UCIe 1.0 based on the UCIe standard. So all the standard, components that are there in the standard have been incorporated into the UCIe model in VisualSim. So all the data flows, all the controls, the sideband, the main band, all of those have been incorporated into the implementation. So when you get the UCIe library, you actually get all of these components within the single package.